Welcome back, Gen Chem 2. This is so exciting. I thought about taking a break for a second, but then it dawned on me, these videos are so much fun that I'm sure, like I said in the last video, oh my gosh, I'm sure this is like Netflix. You're binge watching because they're so much fun. So I've got to push through so you've got more material. So this is our third video on equilibrium. And this is so exciting. I love it. So we're going to start to get in the heart of equilibrium. And we're going to do, oh, what did I do? I don't even know what happened there. We are going to look at some of my favorite calculations. And we're going to get real solid. We're just going to do one problem. But we're going to get solid on our ice tables. Okay, so in our equilibrium in our first two videos, we defined a general reaction. For any reaction, whoa, who erased my moles there? Come on, y'all, you gotta be on your toes. We've defined for a general reaction that we're always gonna look for or be given an equilibrium constant. And that equilibrium constant is always a comparison or a ratio of products to reactants. And more specifically, we include moles, not order, on these. And I just say that because we're just finishing our kinetics. So I want to make sure that we are back to moles on these. So what happens then if you have the opposite of our last video? So we ended our last video where we had equilibrium concentrations, and we calculated our KEQ. Well, let's turn that around. In this video, what if you're given a KEQ value and you need to calculate your concentrations at equilibrium? This is a super valid question. This is going to happen all the time, especially in our next unit when we flip to acids and bases. They have been studied for 200 plus years, if not longer, actually calculated for probably a couple hundred years. So we will have massive tables of K values. We'll have a Ka for our acids and a Kb for our bases. So that's literally going to be known. What isn't going to be known will be our equilibrium concentrations. Okay, so let's turn this problem around and let's see if we can figure it out. So let me give us an equation or reaction. Let's take carbon monoxide and water. And it turns out that that can make carbon dioxide and hydrogen. Now this is a pretty well-known reaction. You'll find this KEQ anywhere. I'm going to go ahead and add a temperature to it. Okay. And I'm going to give us the KEQ. I'm just going to give that away for free. So what if we start with 1 mole of each in a 1 liter flask? Okay, now that's a whole lot. Don't you love chemistry when they just give you wording? All right, so let's put this together. Let me show you how I like to solve these problems. You already know what I'm going to do first. I'm going to spell out the KEQ. Now shut the front door for a second. Is our reaction balanced? Yes. We just got a free pass on that. Don't you love it? All right, so that means I've got carbon dioxide, hydrogen, over carbon monoxide, water. And now that KEQ is equal to 5. Okay, so that's the first part we've just tackled. And now the second part is, okay, if we start with 1 mole of each in a 1 liter flask, that means this is our initial. What is 1 mole in 1 liter? You guessed it. I gave us the complicated math in the video. You know your homework will be worse. That is 1 molar for each one. Okay, now I love a good ice table. So we start with initial. That's a great place to start. That's our I. And then we're going to have some kind of change. That's the C in our ice table. Some kind of change is going to happen. This reaction is got to reach equilibrium first. And so once we undergo some change, at some point we will reach equilibrium. Okay, that's the E for our ice table. Oh, that came out so fluffy. Hang on. So now it's going to be our goal to figure out our concentrations at equilibrium. What? But we weren't given any. We've only been given initial concentrations. So how in the Sam heck are we supposed to figure out the concentrations at equilibrium? We weren't given anything else. Aha. But this is why our KEQ is so important. This relationship will give us that change. It's telling us how much products over reactants will always end up happening. So you guessed it. I love it. This is why college algebra is a prereq to this class. Let's bust out some algebra. So what do we know? We know that on our reactants, we are going to undergo some kind of change. We will lose or react and lose some of our reactants. That concentration is going to go down. And we have a 1 mole to 1 mole situation. So that change will be the same. So I'm going to call it an X. And our X is disappearing. So this is our change. And our change will be the same. Okay, so what do you think is going to happen then on the other side? Well, that's the beauty of equilibrium and reactions, is that they're all connected. So as your CO goes down, your CO2 is going to go up, and so is your hydrogen. So that change is exactly the same. So of course you see why we picked this example, because that change is 1 to 1 to 1 to 1. So it's a good place to start. So then at equilibrium, what will that look like? What will CO look like, carbon monoxide? Well, we're starting with 1 molar, but we're going to subtract some. Same with water. We're starting with 1 molar, but we're going to subtract some. Okay, and then our CO2, we've started with 1 molar, and now we're going to add some. And we have the exact same thing with our hydrogen. Okay, if you're a fan of algebra, you already know where we're headed. So we picked this one because it's a nice example and we've got a shortcut. But our next video, we will not have a shortcut, and we are going to hit some fun. I mean, we're talking FOIL and quadratic formula. You know where we're headed. Okay, so now let's plug all of that in. Our KEQ is 5, and that 5 is our CO2, H2, CO, H2O. Okay, so that means that it is our 1 molar plus X, 1 molar plus X over 1 molar. Oh, that's sloppy, huh? Minus X. Okay, so let's simplify that just a little bit. I'm going to go ahead and take that 5. And I'm going to go ahead and call that squared. And I'm going to call that squared. And now how do I get rid of that? We can take the square root on both sides. And when I do that, I'm left with 1 plus x on the top, 1 minus x on the bottom. And now you get to distribute. So I'm going to go ahead and distribute. Okay. And then I'm going to start to solve for x. So I'm going to put my like terms together. Okay, and I'm going to end up with x equal to 0.387. Okay, are we done? No, but we're almost there. Remember what we just calculated? This is our change. So we need to plug that back in to our table. So let's go back up here. I'm going to write it in pink because I'm just feeling pink. This is our change. So that means that we need to subtract 0.387. 0.387. We're going to subtract. And then over here, we're going to add 0.387. So that means that at equilibrium, let's do that math. What's 1 minus 0.387? What's 1 plus 3.87? Now we have our concentrations at equilibrium. And for fun, you can plug back in and check. And I think you'll notice that I probably wrote a 5 up here, but we might be closer to 5.1. So how do you actually check that? You can plug those numbers right back in, and let's see what you get. And you should get darn close to that KEQ. All right, I'm gonna actually stop this video, but I want you to watch this as many times as you want, because in our next unit, we will write ICE tables in Unit 3 and Unit 4 a million times over. So I wanted this video to be nice and short, just to show us what an ICE table looks like. And then our next video, we're going to turn right around and write some more ICE tables. The only difference is we won't be able to use this shortcut. So what happens if you can't take that shortcut?